So we're just going to go through the 10 rules that we have for electricity. I'm going to start off very simple with number one. If you have negative to negative, then that means that you'll have repulsion. So if you've got negative to positive, then you'll have attraction. Positive to positive, you'll have repulsion. Negative to negative, you'll have repulsion. Okay, it's just a rule of thumb. Idea number two then, if I wanted to draw a cell always has a positive pole and a negative pole. If I put something next to the negative pole, then it is going to repel. We can play around with that idea then. So let's say this was a 1-volt cell and I added two 1-volt cells together in series. Then I'm going to double the amount of push that's coming from my cell. If I put something negative next to that, then it's going to repel more. Remember that the negative stuff that we're talking about here are electrons. So the symbol for an electron is an E with a little negative sign over the top. So in both of these instances, we've got the movement of electrons. And if we then imagine that this is through a wire, then that's how electricity works. Idea number four uses the idea of electrons. So one electron by itself is actually pretty useless. You need billions and billions of those electrons all moving at the same time for something useful to happen. So just like we don't talk about having one crisp when we go to the cinema or one piece of popcorn, we think about there being packets of crisps and packets of popcorn because, let's face it, who's going to just want one piece of popcorn? One electron by itself is useless. A coulomb is a packet of electrons, and then this is our foundation for the rest of the ideas. So we're going to be using this symbol, a circle with a negative through it, to describe the rest of electricity. Idea number five then, what's the point of moving electrons? Well, electrons are carriers of energy. So this coulomb is able to carry energy, and it's the energy transfer system in electricity. Let's just say that this electron was carrying, this packet of electrons was carrying 5 joules of energy. Then we'd be able to say that it has 5 volts. And it doesn't matter the amount of coulombs that are carrying that energy. If I have 2 coulombs that are both carrying 5 joules, then that still counts as 5 volts. It would mean that whichever cell in my system, or battery in my system, is giving a potential difference of 5 volts. So that's the definition of voltage then. 1 volt is when 1 coulomb carries 1 joule. And there's a very important word that we use for describing this, and it's this idea of per. Per means for each. So the definition of the volt is 1 joule per coulomb, or 1 joule within each coulomb of charge. And remember as well that we can write that as its formula as well. Idea number 6, we're using the idea of coulombs again. So if I have 1 coulomb of charge that is moving at a rate where I've got one of those packets of charge passing through my component every 1 second, then that's the same as 1 amp. If I was to have 2 coulombs of charge per second moving along through my circuit, then that would be the same as 2 amps. Okay, so there's your basic 6 ideas. Just to make it a little bit more interesting, we're now going to start applying some of those ideas elsewhere. So idea number 7 then has to do with the whole system that we've been looking at so far. So I'm going to draw here a wire, cross section of a wire, and we're going to put inside this wire a little electron. I'm just going to have 1 electron in this example because, quite frankly, it's easier to draw. And then what I'm going to have is I'm going to have the nucleus of an atom. Okay, so this small black dot is going to stand for my nucleus. Now my electron is going to move through this circuit, and every now and again that electron will collide with the nucleus. Remember that collisions mean transfers. So if there's a collision between your hand and somebody else's hand, then you transfer energy. In this case, the kinetic energy inside this electron is going to decrease after it collides with the nucleus, which means the kinetic energy of the nucleus is going to increase. Now I'm just going to focus on the electron just for a minute. We're going to talk about what the electron is going to do. So if the kinetic energy of this electron decreases, and we know that the equation for kinetic energy is 1/2 times mass times velocity squared. If this kinetic energy goes down, this constant number doesn't change, My mass doesn't change. The only thing that can change is my velocity, which means that the rate of flow of this electron, the current, is going to decrease as well. Things are a little bit more interesting for my nucleus, because if its kinetic energy goes up and it's unable to move, because remember that this is a lattice, so these nuclei are vibrating in fixed positions, its vibration is going to increase. Now, if that vibration increases, if that kinetic energy increases, then there's going to be two consequences to that. First and foremost, the temperature of the nucleus is going to increase, because remember that temperature is the measurement of temperature is also the measurement of movement in a circuit. If the temperature increases, then that can have effects on the amount of energy that's being wasted, the heat of the wire. Is it going to overheat? Is it going to short circuit? We put that to a conversation for later. But right now, all we have to remember is that the temperature is going up. And the other thing is that as these nuclei inside the wire are vibrating more, there's now a greater chance that this nucleus is going to have another collision, which means that overall the rate of resistance is going to increase as well. So this is our explanation for resistance. Resistance opposes current, so resistance increasing will cause a decrease in current, and this is the reason why. Idea number 8, then, we are going to be thinking about putting all this together into one nice idea, this idea of what power is. Power is the energy per unit time, so the amount of joules per second. There's a couple of different ways that we can calculate this. We can either have the amount of energy that's transferred and divide that by the time in seconds to give us our overall wattage. 1 watt is when there is 1 joule of energy transferred for every 1 second of time. The other thing we can think of is we can bring in these two ideas that we have above, this idea of current and this idea of voltage. So remember that current is the number of coulombs every second, and that voltage is the amount of energy per coulomb of charge. If I want to find out the amount of energy that's being transferred every second, and I have my current and I have my voltage, then I can make a little mental model like this. I want you to imagine that we have a current of 1 amp and we have a voltage of 2 volts. That means that I've got 1 coulomb of charge passing through my component every 1 second. If it's 2 volts, that means that my coulomb is carrying 2 joules of energy. So if I put these two together, then I can see that I've got 2 joules of energy in each coulomb being transferred every 1 second, meaning that I've got a power of 2 watts. So the equation for power is I times V, and that's what we've shown here. That's idea number 8. Idea 9 and 10 then are to do with series and parallel circuits. So I'm just going to draw a really simple series and parallel circuit. And it may not look perfect, but it'll be good enough for government work. I'm also going to draw a very simple parallel circuit. I'm going to have 1 cell, and I'm going to have 2 bulbs in parallel. Now remember, this works for bulbs, resistors, motors, whatever it is that is in series or parallel. Now, this means understanding the rules for current and for voltage and for resistance in series and parallel circuits. You have to understand all the ideas that we've gone through so far. It just makes it easier to do that. I'm going to start off with a series circuit, and we're going to start talking about current. In a series circuit, the current is always the same no matter where you look in your circuit. So if I pop an ammeter here and I pop an ammeter here, and if this was to measure 2 amps of current, this ammeter over here would also measure 2 amps of current. And basically the reason for that is that there's only one pathway, there's only one loop that my electrons can go through. So it's a little bit like there's only one road that your cars can drive on. So if I've got 2 electrons side by side, this electron, as it is pushed by the cell, the potential difference is going to push into the next electron, and they're going to move around at the same rate. In a parallel circuit, the current splits when you get to a junction, and again, it's a nice idea to think about the coulombs per second being cars per second on a road. If I was to measure my current here with an ammeter, and I have 3 amps of current here, that's the same as saying 3 coulombs for every 1 second. But instead of coulombs, let's think cars. So here's a road with 3 cars every second on it. I'm going to change the resistance of this light bulb ever so slightly, meaning that there's going to be 2 amps in this light bulb and 1 amp in this light bulb. This 3 amps will split into into two different pathways. 3 cars per second moving down the main road, 2 turn off down this road, meaning that 1 will split off and go down this road. 2 coulombs per second in my circuit up here, in this initial ammeter. There are 2 coulombs per second down this pathway, meaning that 1 coulomb per second will go down this pathway. The rules for voltage, then, we have to remember that the amount of voltage, the voltage of any system, is the amount of energy being carried by each coulomb of charge. And remember, energy can't be created or destroyed, just transferred from one form into another. So if instead of electrons, and I think of these as packets of electrons, or coulombs, these coulombs are going to be carrying 10 joules because it's a 10-volt system. If these coulombs then interact with this bulb, they're going to have to share the energy between this bulb and the other bulb later on. Because remember, these components are wired in series. So my coulombs interact with bulb number 1 and then with bulb number 2. So let's just say that this particular bulb is given 2 joules per coulomb. That means that the other bulb over here is going to get 8 joules per coulomb. So it's a 2-volt bulb and an 8-volt bulb. So in a series circuit, the voltage is shared. It's shared not always equally, but will always be shared completely by whichever components are in that series circuit. The voltage in a parallel circuit is ever slightly different, but all you have to remember is this idea of coulombs carrying energy. We'll say that this is also a 10-volt cell. And I've got a coulomb of charge here. It's going to be carrying 10 joules. Now remember, though, that these coulombs are going to split. So coulomb number 1 up here it might move through either one of these 2 pathways. It can either split at the junction and go to bulb number 1 here, or it can split at the junction and go to bulb number 2 here. I'm going to say that this coulomb of charge is going to go down the long pathway here. This other coulomb is going to go through the shorter wire pathway here. This coulomb of charge is carrying 10 joules because it's a 10-volt cell. That means that this bulb is going to get the full amount of charge. This coulomb of charge, the brown one, is also carrying 10 joules. And because it's split, it's not having to give its energy to any other components, meaning that this bulb is also going to be able to get 10 volts. So the voltage in a parallel circuit will be the same across both pathways. If we have got 2 bulbs here wired in series, then it will be shared between those, but the voltage will always be the same across pathways. And the last thing we'll look at is the resistance. So the resistance in a series circuit, the number of collisions, the amount of collisions that are happening in between those electrons and those nuclei. If you add components on, so if we increase the amount of components, and I'm just going to say bulbs just for this example, if I increase the number of bulbs, then I'm going to increase the resistance. Resistance is going to go up. So we can imagine our electrons here, they're moving through these components, they're through these wires and interacting with these components. There's going to be a certain number of collisions. If I add another component in, then my electrons have to interact with another component, and so therefore will increase the number of collisions. The resistance in a parallel circuit is slightly different. So because the resistance in a parallel circuit will change depending on pathways, actually adding in components in parallel pathways is going to decrease the overall resistance. When you think about it, like a lunch queue. If there's only one place where you can buy your lunch, and there's 1,000 of you all trying to get your lunch at the same time, then it's going to take you a certain amount of time to pass through that lunch queue. If we open it up to 2 queues, then there's more pathways for the same amount of people to pass through. So it's going to be a more efficient process. The rate of flow of pupils is going to increase. If I open up a third one, then there's even more places where my electrons can flow through. I've increased the number of pathways that my electrons can flow through, and so therefore I've decreased the resistance. I've decreased the amount of collisions that are occurring. My currents actually, my resistance is down. So that's idea number 9 and idea number 10. Series circuits and parallel circuits bringing together everything at the same time. Okay, thank you very much.